Which one?
You have to bring them down, the
So,
curtains.
do we?
We used to do that every time.
Okay, I see that there's something still not okay in the cameras. I think it looked that it's pointing incorrectly, a little bit incorrectly. Yeah, yeah, it helps. That definitely helps. Good.
So now you're live.
I'm live, yes. What about this guy? No, that's not on.
Ah, 5 seconds of some screen. Then
Project the lamp. How can I put the projector on?
PC video lights off. Lecture.
Yeah, yeah, this one. So it's HDMI one. Very good. Okay, so last thing to do is that you just need to
Just not so.
can you stir that a little bit of down and a little bit of right?
Wait, go this way or that?
Take a look at from the camera. So I mean that from your phone. So you see that is a little bit off. So it's that though. I don't know why is it that I don't see. I'm not able. You don't. Let me take a final thing.
It doesn't change.
Is it froze somehow?
Yeah.
Yeah, it is. Okay, now it disappeared completely. So can you check that the cable connection is okay?
I'll reconnect that. And
Hmm.
um, this one.
Yep, we found it again. All right, I think it is very good. So it's gonna be like
Yes. And
this. What about this guy saying nothing?
can you stand up in order to
Sure, I think it is perfect now.
wait a few seconds?
Yeah, it is perfect. It is perfect. It's really, really good. So only problem is that maybe we all need to go online.
So you have to start projecting.
Oh yeah, yeah, here. Still no. Duplicate.
And I believe we have lights from here because it's gonna decrease the quality of your picture.
Yeah, you need to put a little bit more lights. Yeah, that I think it is okay. I can still play with. No, it's very good. It's very good. still the problem is that this overhead projector is that the HDMI one. I think that it was already displayed.
Projector is cooling.
No, no, don't put it in a cooling.
No, it's cooling. Like I didn't do anything. Should we use PC or lecture?
No, this is nothing here.
Yeah.
So it will take another 30 seconds before we're able to put it back. So online participants, stay tuned. So in what is it? The 45 seconds we are able to go. We're good to go. Very good.
Yeah.
Why is that? Why is that they're following online? Okay. Maybe it makes sense to stay online because right now the material we're covering is going to be something that is not as challenging, theoretically as challenging as many other cases. So, but why is this device is saying nothing? Warming up. So it's still in a warming up phase.
20 seconds.
20 seconds, we are ready to go. By the way, so most probably, well, actually, it's going to be next week. Today is the 21st of March, right?
Yes.
So I'm going to explain stuff related to, yeah, there it is. Okay,
But I have to listen like intro.
yeah, please do that. So we have most 10 people online, and what is it, 110 people here in a lecture room, so it's a really, really crowded. So those of you that are online, you're really lucky, so you don't need to squeeze in here because there is no available seats really.
So few things. When do you think it will be
So
finished?
it's going to be at 1:45, 1:45.
Ah, okay, great.
All right. So, like I said, what's going to happen is that next week, which is the 28th of March, we're going to discuss a little bit about the fatigue analysis, but also we're going to discuss about the career counseling. So that's going to be something that is not exactly the curriculum of this course, but I would like to spend some time. Hey, welcome. And like I said, that online participants, they made a good call because this place is crowded. So it's hard to find a place to sit. All right. So week from now is could be a little bit career counseling, but there's also going to be how is it we can handle the fatigue analysis based on the multi-body system dynamics. I don't know if you guys have participated in a class entitled Fatigue Design or Fatigue something. So you've been there. So the most of the things that I'm about to explain will be something that you know, at least you have some level of understanding. But basically, we're going to focus on how is it the loading can be introduced, because that's usually the most difficult part of the fatigue analysis. You can do the analysis as far as you know what is a loading condition. And the loading condition is not at all easy to define. So we're going to discuss about the loading condition a week from now. But today we're going to focus on mass invariance, contact modeling, and stress analysis. Stress analysis is already taking you a little bit in a direction of fatigue analysis because stress history will be the part of the fatigue. And then we're going to discuss a little bit about other subject matters like product lifecycle management and the biomechanics. And then I'm back with the future of simulation, an extra lecture, which I'm not clear or is not clear to me what will be the subject matter on April 25th. So that's going to be our schedule for period number 4, which is same time the last period of this year. Welcome. As you see, Can you guys make a room a little bit so we can get the one extra seat here? All right. All right. Very good. Very good. Okay. Prior to moving on to real deal, let's summarize what was the deal about the Craig-Bumpton mode. And the Craig-Bumpton mode was used and introduced because it's a general approach. It allows you to take a loading and constraints into account that otherwise will be a big headache because you need to define how is a boundary condition in final element modeling and make sure that the boundary condition match with the joints you're using in a multi-body system dynamics. And it sounds like it's doable and it sounds like an easy thing to do, but in reality it is a little bit of a challenge. And also you need to consider when you're using the boundary condition and when you're using eigenvalue analysis, another thing that is a bit of the problem is that when there is a single point force imposed to a structure, that usually needs a special treatment as well. All that can be addressed by using a Craig-Bumpton approach. And as we discussed a week ago, idea of the Craig-Bumpton approach is that you will take your all the Noether degrees of freedom, you categorize them into two different categories. The one that is called as a boundary degrees of freedom, and rest will be automatically called as interior degrees of freedom. Once you make this decision, then everything after that will be automated. And automated, what will happen under the hood is that your finite element software will reorganize your mass and stiffness matrix and its corresponding Noether degrees of freedom such that this boundary degrees of freedom will be located in upper right corner of your stiffness matrix, as is the case of mass matrix as well. And then you go. And then you conduct an eigenvalue analysis, which you're only going to use this interior degrees of freedom. And then you're going to conduct something that is giving you static correction modes, and that you can get by introducing unit displacement in the direction of where your boundary degrees of freedom are located at, one at a time. So you do that, you get the modes that are not orthogonal. That they are not orthogonal because of this unit displacement that is shown here. Oh, excuse me. The drawing seems to be not yet activated. No. Is it another Ben or what? Okay, I don't know why, but I'm unable to make a drawings. So that's okay. So you see that the static modes that you can see in the lower left corner of the slide are not orthogonal. So meaning that they are not independent with respect to each other. So they have certain similarities, as usually is the case when you're introducing unit displacement. Eigenvalue analysis is a special case because what you can get as a result of an eigenvalue analysis is a modes that are completely independent from each other. So they will be forming an orthogonal space for you. And the orthogonal space is giving you a clear advantage. And the advantage is that then once you use those modes, your stiffness and mass will be diagonal, meaning that it will remove these connections between the degrees of freedom. So that's what the orthogonality means for you. All right. So now we don't gonna get the orthogonal modes, but to fix this problem, we can take these matrices and compare the stiffness and mass again. And now we will get the matrices that are not diagonal yet. But again, when we're going to use another set of eigenvalue analysis, which is called orthonormalization, then you will get something that is completely diagonal. Now that's it. That's about the Craig-Bumpton. And my question to you is this. Craig-Bumpton method is often used approach because it allows to describe local deformation due to the forces and joints. It can be used for beam-like structures. It can be used for plate-like structures. It allows to describe the structural damping. Okay, so here's the deal. So each of them are correct. Yes, it can be used for beam-like structures. It can be used for plate-like structures. But what's the unique feature? Why it is superior versus, let's say, landmass approach. So one only is correct. One option only is correct. like it says, what it is often used, what makes it user friendly, or let's say application friendly. That would be the better way to say it. So what makes it application friendly? Okay, so should we take a look at this already? Now Socrative should be open, isn't it not? It is open. So should we take a look at that, or we are? Can I continue and get back to this in a minute? Or would you like to get an? Uh, would you like to get some kind of like a hint? Maybe you don't want it, but I'm gonna still give it to you. Remember the whole story about the method is that you will do this selection between the boundary degrees of freedom and interior degrees of freedom. And what you're gonna do then with the boundary degrees of freedom is that those are the points that are giving, you're gonna give a special attention to those points. Because in those points, when using this method, you can introduce joints and forces more accurately than otherwise you would not be able to do. So that is a story behind of the Craig-Pompton mode, of Craig-Pompton approach. So again, boundary degrees of freedom, they should get a better name, which is a point of interest. Point of interest in a sense that this is where one can introduce joints or forces. So that's what it means. And now it's giving a special attention to make sure that you can introduce the forces and joints in a correct manner. That otherwise, I think you can do it otherwise too, but it will be very much case dependent and it needs an awful lot of thinking. So it's not automized as is the case of Craig-Pompton. All right. Now, here are the few notes. You know, in theory, the element type can be selected without any limitation, but I think that it really, most of the cases, the kind of the structures and the element types that are used are solid elements. You know what the solid elements look like. So it looked like a brick. And using these bricks, you can describe pretty much any shape you want. But then it comes with the difficulties because there may be a beam-like structure with the hollow cross-section. And if you started to use these solid elements to describe thin structures, you need to have them a lot because you are not allowed to distort much your element size, I mean shape. If you have this brick shape, it should be roughly the brick shape. And if you make it be really lengthy and very thin, your accuracy will get compromised. And if you have that kind of thin structures, maybe sometimes would be better to use a plate element instead of solid elements or beam elements. But again, in floating frame reference formulation, you can use any kind of elements you want. But the beam structures, sometimes it's okay to use just a landmass approach because they are so simple. Now, one thing that is important is that when you're using this orthonormalization procedure, you will get modes that are describing this local deformation and the modes that are roughly the free modes. Those free modes, you need to take it away from the set because free is describing the rigid body motion, meaning that there is no deformation there. It's like a beam that is moving up and down, left and right, rotating like that without deformation. That's the deformation mode you are not allowed to use in the floating frame reference formulation. And why is that? Because the reference motion is already captured by reference coordinate system. So if you would use them, that will be double standard. That will be too much for one thing. And that's why you need to take these rigid body modes away. All right, and then as mentioned, you can use pretty much the same kind of structural models that you're using structural strength analysis here when you're describing flexible bodies, because only what matters is the number of modes, not the number of initial nodal degrees of freedom, but what is the number of modal degrees of freedom. That's the only one that matters. Now, you guys have never perhaps heard about these symmetry models, have you? But when I was younger than I'm at the moment, then the computational power was limited. And it was very much in a fashion to try to create the models that was not representing the entire structure, what one half of it, one fourth of it, something like that. And then you were using the boundary condition to describe that, okay, this is just a half of the structure. And why you would do that? Because then you will save a computational power by half, by four, by divided by four, or whatever you want. These kind of symmetry models are not so much in a fashion anymore because you have a lot of CPU power in your disposal, so you don't need to care that much about it. But if you use them, then you're not allowed to use this kind of the models in your flexible bodies. Or in the floating frame reference formulation, rigid body modes need to be removed because rotations are assumed to be small, because deformations are assumed to be small. Reference coordinate system takes care of the rigid body motion. Damping is assumed to be insignificant. So you guys know the right answer? You know the right answer. Very good. Okay. And then, oh, okay. Yeah. Sorry. My mistake. So I need to take this off for a little while and take myself here. So this is going to be the result of, hold on. So what do you think about the success rate here? 70. Seriously. So where is the team spirit, guys? So 100%. It's 100% because we need to, remember what's the most important thing for us? Can-do attitude. So it must be 100%, but I'm thinking here it is 100%. So we have 17 answers here. There, okay. 70, you can say 70%. Okay, so it's going to be, I'm saying 100. And if I'm going to win, what's going to happen then? So you guys need to dance for me, right? Okay, anytime would be good for me. Anytime would be good for me. So just let me know when is a good time that you would like to do the dancing performance. 100%. Very nice. Very nice. Okay, so next one. So we need to get back to this because I'm not gonna forget it. Like you did not, for me. I, okay, so online participants, make sure you're starting to prepare yourself the dancing performance for your own choice. You can choose whatever, what kind of a. But I would like you to know that I like the breakdance. All right, so the next one is the in the floating frame reference formula. So rigid body modes need to be removed because of what? What is the reason for that? And I'm going to leave that to side and I'm going to continue my presentation by taking myself here. All right, it looks that is okay for, yeah, everything is okay. The drawing is still not possible. I don't know why it is not possible, but this is what we discussed a week ago. So the selection need to be based on your engineering understanding. That's about it. And these are the different deformation modes. Like this kind of deformation mode, for sure, if you have a loading in this horizontal, I mean, this up and right direction, this kind of deformation mode is very, very important. But then this kind of deformation mode you see here, first of all, you see that the frequency is very high, probably not so significant to you. And then there's going to be more exotic modes like we discussed earlier. So it's all about your engineering knowledge, your engineering knowledge. And like mentioned earlier, there is this automated way that you can put the threshold value, meaning that if the contribution is less than predefined threshold percentage, then you will be ignored. I mean, one mode contributing less than the predefined threshold value, you will be automatically off. But remember, this is valid for analysis that is already conducted by using all the modes. Then you can make this selection, not by, that you do the one kind of the analysis and then you're gonna change the work cycle, then you need to redo the whole thing. All right. Here's the verification tips. So compare the inertia properties, how much the body weighs, how is the inertia behavior as a pendulum would be a good test. Compare the natural frequencies and compare the deformation. You can introduce artificial static deformation, and that should match with the one that you can get from the finite element software. Those are the verification tips. And now I would like to spend another 10 minutes, 10 minutes only, about the mass invariant. So it's not going to be more than that, but I'm going to take a timing that it's going to be just 10 minutes for mass invariance, and there's going to be a question in class quiz right after, which is asking what is the role of the mass invariance. Role of the mass invariance is to combine deformation and reference motion. Remember what we did here. We started from the concept that we have multi-body system dynamics and the finite element model. And we put them together. And when we did that, they need to be coupled one way or another. And generally speaking, you could do the coupling in using the elastic forces or inertial forces. And what we're going to do in the case of floating frame reference formulation is that we're going to couple them by using inertial forces. This coupling can be as strong as it can be theoretically, or it can be a little bit loose. And that how strong is a connection is defined by mass invariance. So the role of the mass invariance is that it combines deformation and multi-body system dynamics. How strongly? That you can define. And it is amazingly enough, this is a decision that the user can make, which is weird because this is very fundamental decision. But it's allowed user to make this decision because if you're using loose coupling, you can gain a lot of computational efficiency. That's the benefit. But you might lose a little bit of computational accuracy. Problem is, it's unclear how much you're going to lose your computational accuracy. And that's why it's a little bit of a risky game to start playing with the mass invariance. But as the title implies, mass invariants are something that you're computing prior to simulation. And then it's your selection which one of these mass invariants are taken into account, which one of them are ignored. And again, it's about how tight or loose is this connection. All right, story that I'm about to explain is unpleasant, very theoretical, but keep this big picture in your mind all the time. It's going to be unpleasant because we need to get started from kinematics. Big problem, because if the kinematics is changed, you know what's going to happen to you. Everything needs to be changed. Because remember, in the dynamics, we have one step only that we need to make, one decision only that we need to do. That is, how is that we defining kinematics? Kinematic is that how is that we defining each of the particles in our system? And yes, you can do that in numerous different ways. But once you make your mind, then rest is mechanical. Mechanical in the sense that then you're going to use a concept of virtual work or using energy minimum or whatever you want, and you will get equation of motion. But it's all based on what is your selection of how you're defining your particles. Remember, we made this selection when we first met. Remember this motional time we first met? Almost a year ago. And we had the first lecture that was in simulation of mechatronic machine. In first lecture, I say, can we make an agreement that we can use in the body reference coordinate system? And then you were saying, yes, we can make this selection. Now we need to come back to this first lecture. Yes, we're going to use this body reference coordinate system, but there's going to be an additional component due to the deformation. And because we change in the kinematics, we have to change everything that is related to equation of motion. That's going to be a big process. We're going to cut the corners. I'm going to explain that like I promised now in 7 minutes. All right. But again, this U bar F is a problem maker. is really a bully. He's a big bully. And the big bully is going to make, but this time we just need to obey the bully because if we want to take this flexibility into account, that's the only way. So it's a big monster that now comes into play, and we just need to live with the monster. All right? And now the monster can be expressed also by using these modes and corresponding modal coordinates. So it's a matrix of modes and corresponding modal degrees of freedom. Now, our vector of generalized coordinates becomes to be much longer than it was, because it was in a planar case just R1, R2, theta. But now we have the number of deformation modes that too need to be solved. Okay? Still, this is our kinematics. In the special case, this is how the vector of generalized coordinate look like. So it's going to be R1, R2, R3, thetas, 3 or 4, depending what is the choice of the generalized rotations you wanted to introduce, and then the p's as many of your modes. Okay, and then we continue this story here. Now what we need to do next is that we need to compute these nasty velocities and acceleration. And we need to be able to express them in a way that we extract generalized coordinates from our velocity and acceleration definition. All right? Don't get confused about the details again. It's just a velocity. It's still our friend. But now it looked different because, this monster came into play. So it looked a little bit different, but it's still our big friend of velocity. Okay? So, velocity, when I take a look at this thing, remember what we did last year. We say that this vector u bar dot is equal to 0 because there is no deformation. We cannot do that anymore because there is a deformation. And when deformation is described, too bad that I'm unable to use my pen. Let me try one more time. No. What is it? What is this with? Oh, I should be using this kind of a presentation mode. Just a second. U bar dot is going to be like this. This guy here will be equal to 0, but this guy will not be. All right, let me see if there is a way that I can do it. Drawings. Was it like, just a second, I think it is going to be like this. All right, you will see that in a second. Yeah, I think this is the way that I could, yep, there it is. Yep, very good. All right, now I have everything. So this is my velocity, and then I'm using mathematical manipulation to express my velocity as it is shown here. Not a big surprise. And look at what I have here. I have my skew symmetric representation. You know what the skew symmetric is, that you just take a vector, take vector components, and you place it as shown here. So you will take a third component, you put it in a minus sign here, second component as it is here, first component in a minus sign here, and opposite way in a lower right left corner to your skew symmetric matrix. So that's it. And you continue then. And when you continue, you're going to describe your acceleration. Now the acceleration consists a total of 5 components: translational acceleration, normal acceleration, tangential acceleration that we discussed earlier. But now we have a Coriolis here, because by the definition, Coriolis takes place when a particle is moving in a rotating disk. Now the movement is due to the deformation. And then we have a acceleration due to the deformation itself. So it's a big mess, and it becomes the reversed. Now, this is how the acceleration look like. This is this magical mapping matrix. When you put everything together, it's going to be a big, big mess where there's a mass matrix and quadratic velocity vector. And finally, when you take a close look about your mass matrix and, well, quadratic velocity vector we don't, your mass matrix consists of six different components. Six different components. And it is this bad. But there's one thing that helps your life, and that's the fact that some of these components, or let's say subcomponents, you have in these six components can be pre-computed. And these pre-computed ones are called mass invariants. They can be pre-computed because, like the title said, they are invariant. They will not change during the simulation. So that's why you can do this pre-computed. And now comes the difficult thing. So there is a total of, let me see how many invariants. We have 9 different invariants. Each of them has a clear, not clear, but kind of the physical interpretation. The physical interpretations are, let me see if I have it. No, I don't even have it here. But this is how you can compute them. And the big challenge comes here. This is a screenshot from my Adams software that we used earlier to do the simulation assignments. In Adams software, you can define how many out of these 9 components you're going to keep in the play and how many of them you will kick out. This is a very hard decision, but comes with the decision that comes with the benefit and a drawback. The benefit is that you can gain a lot of computational efficiency. Drawback is the problem that how much you're losing the computational accuracy, you don't know. Because at least I cannot tell, if I take this component, whatever that means physically, and ignore it, how much it's going to affect my results. So my advice to you, keep everything active and face the fact that it's going to be computational a little bit slower. It's still going to be okay, but a little bit slower. Okay, role of the mass invariance is my next in-class quiz. And the options are, it allows to describe the structural damping, allows to describe externally applied forces, coupled stiffness and damping, coupled finite element model, and multi-body system dynamics. So which one it is? We'll do. We'll do that now. Okay, so here's my. Okay, this is a second in class quiz. Success rate, please. Okay, I got the success rate guess. I think this was related to previous one. That was 88%. But what about this time? Second in class quiz. What's the success rate? 100%. So now you're all saying 100%. You know what? I'm saying 70. So who is correct here? So let's see. Let's see. Okay. So, okay, you guys don't see it. Okay, let me, how can I put this on? Okay, here it is. 95. 95 is really, really good. But not 100%. You're right about that. So not 100%, but it's high. Okay, so floating frame reference formulation, rigid body modes need to be removed because reference coordinate system takes care of it. So no double use. All right. The next one is this one, role of the mass matrix. And then we're going to move on to contact modeling. Okay, what do you say about the success rate this time? What about online participants? What is your guess about the success rate? Okay, I got the information that their audio stream is not as good as it could be, but I think it is, as I don't see any complaints, I think it is okay. I hope it is okay. Okay, so what's the success rate? 100. Okay, I'm with you now. So we all gotta say 100%. So 100%. The last time I think it was 16 student, one six student. Was it 20? Okay, so now we got 14. So yep, 16 students, and then the contact modeling, something a little bit different. Okay, 17. So we're still waiting. What is it? Three more, or two more, or one more? 20. Okay, so the last ones, speed up, please, so we can close this one. Why is it we get this many students? Because usually it's less than 20. No. Okay. Okay. But it seems that we're only going to get 17, so I'm going to close this now in 5. It's going to, because of the delay, this counting makes no difference. So I'm going to just close this thing. We'll see then. Aha! Oh my God. So now we scored really low. So what happened here? Because, so let me take myself back here. Role of the mass invariance is nothing to do with the damping. So it's all about the inertia force. It's not related to damping here. So it's not actually describing external applied force. It's not describing structural damping, but it couples the description of deformation and multi-body system dynamics. So that's option number D. All right. And then I'm going to take myself back to this presentation mode that allows me to do the drawings. So just a second. This one. Okay, so let me do the counting. So it's going to be is it like 2 more lectures that I'm going to deliver, and then that's it. So here I'm going to focus on this contact modeling today, and if we have any time left, we're going to discuss about how is that we can possibly describe stresses from multi-body system dynamics. But prior to that, contact modeling, which is very often used as subject matter that is not only in a multi-body system dynamics, but in a finite element modeling, in nonlinear dynamics, basic nonlinear dynamics, in many other disciplines. There's a lot of things that are related to contacts. Games is a good example that you need to deal with the contacts. Like I say, last week, so we have two choices to make. But let me get back to that. So when we deal with the contacts, there are 2 steps that need to be taken. So the contact detection, that is a big part of the computing. So you need to be able to detect whether or not there is a possibility of contact, or if there is a contact that takes a place. Let's say that you have 2 beds and they can contact, but are they contacting or not? That's going to be your first question. And if I just gonna compute each of the particles in this band and each of the particles of this band and measuring the relative distance, it becomes to be not so trivial thing, because these bands can contact many different locations, many different particles can have a contact. So the first thing that you need to find it out is that how is a contact? Is there a contact or not? Contact detection is the name of that first step. All right. Then you see, okay, there is a contact. These 2 pens are in contact with each other. Then you need to do something. And the choices that you can do is that you can introduce a force. That force actually rapidly comes between these 2 guys and separated them. Or you can use inequalities, which is kind of like a constraint that we're dealing when we introduce in the joints. But the inequalities are, the constraints are in a form of inequality, something that we can say that these pens can do whatever they want, but they cannot penetrate. And there's a big difference between these 2 approaches, because if there is a force, this force is always behaving in a smooth way. And when you look at that in a very detailed way, it's going to be smooth. Let me just try to make a drawing to you. So if you have a surface here and the ball, The ball is dropping to this surface. That's where the contact will take place. So now in this first method, we allow this ball to come in contact of the surface, and based on the amount of penetration which is here, we're going to separate them by using a force component. Or we can say that this graphics, boundaries of the ball, they can do whatever they want, but they always have to be more, equal or positive than this surface coordinate here. So once they come close it, this constraint will be activated. And this constraint is saying, okay, now you need to stop. You're no longer able to move from this on, and it will be taken away. So those are the two different ways. Okay, so contact modeling, the first step is contact detection. And this is from the really old game. What was the name of the game? I don't remember this anymore. Well, remember, have you seen this? But this game was something that you were able to make some pretty serious deformation and damage to your car, your rally car. I don't remember the name. I used to like this a lot, but because now I'm old, so I don't play games anymore. I don't know why it is like that. But it seems to be that you gain experience. Polite way to say that you become to be old. You don't care about the games anymore. Don't know why. Can explain that to you. Okay, now this guy is not willing to play. Let me try this way. Okay, there was a contact between the car. Ah, you don't even see that. There's a contact between the car and television. You see based on the television that this is not the latest technology because this is not the flat screens TV, but something else. So these are the contacts from the game technology. All right, so, and this is pretty much what I just already explained to you. So let me take myself to this with you. All right, so we have two steps to take: contact detection and contact event modeling. And now in a contact event is roughly two different approaches: non-smooth or smooth dynamics. But the first thing is a contact detection. And the contact detection is something that there is a method that is well developed that is called bounding boxes. And the bounding boxes is a simple concept. It goes such the way that you surround your object that can contact by a boxes. You put the big boxes top of the object that can contact. And then you start to look at these boxes, whether or not they are penetrating, whether or not they are sharing coordinates in a way that they are colliding. So just to give you an idea. Now, you see what is in the middle of the slide is a one part of this Harper crane that we looked a little while ago. Now, there could be a one big box where inside of the box there is an entire ship, big ship, very big ship. And that there's another box, which is an entire container, including the device that is holding the container. That's within the another box. Now you have two very big boxes. You're looking whether or not these big boxes can collide. Yes, you recognize they can collide. What happened next is that you're moving down in your analysis. So you're moving, there's something that is branch level, meaning that there are going to be smaller boxes inside of the bigger box. The smaller boxes could be like, for example, if you take a look at this container holder, there's a smaller box that is located these devices that are holding this container. That could be under the smaller box. Now you're moving to another level. You're checking whether or not these smaller boxes are penetrating, colliding. Yes, they too are colliding. Then you're moving the final level, which is a leaf level, which is a drawing symbols. You're taking a look. Yes, this drawing symbol is obviously colliding with another object, and that you can recognize that there is a contact that takes place. But with this very simple procedure, you're saving off a lot of CPU power because think about the game, a rally game, and you're driving a car, and there's a front bumper in your rally car. This front bumper can hit a tree that is 5 meters away from you, but it also can collide with a tree that is 5 kilometers away from you. And now, if you're going to build an algorithm that is checking each possible contact, there's going to be a lot of possibilities. That becomes to be overly complicated, becomes to be too heavy to do in a practice. Now, with these bounding boxes, you make it feasible, you make it doable. So that's a technique. And now there's a different kind of bounding boxes depending how you put your object inside of the box. They could be object-oriented bounding boxes, or they could be axis-aligned bounding boxes. It doesn't really matter what you're going to do, but the big idea is these boxes, and inside of the boxes you have a smaller boxes, and then inside of the smaller box you have a drawing symbols. That's the analysis you do. Okay, it's based on the bounding box method, very often used. Chem technology use that as well. All right, then comes contact itself. Now, if you would be dealing with the flexible bodies, it becomes to be somewhat simple. You just, take everything into account in a way that there are two deformable bodies cannot penetrate to each other. And that would be very realistic way to describe the deformation. But multi-body system dynamics games and many other applications, we actually can afford to use these deformable bodies. So we have to take this deformation due to the contact into account by an alternative way. And this is what we call indentation. Indentation that is not really taking a place, but it's like imaginary deformation. Because if I take myself back to this, all right, I think that I'm not able to make any drawings this way, but let me try to change this a bit. Was it this? No, sorry. Okay, so this is not the correct slide, but again, here's the surface, here's a ball that is coming down. So what's going to happen to, I don't know, maybe this surface is made out of concrete, so it's not the significant deformance you can see here. But as soon as the ball contact, let's say the pressure inside of the ball is very low. So what's going to happen? The ball is going to be something like this. So the ball would make a deformation like this. That would happen in reality. What we are doing is that we are assuming this ball to be rigid, so obviously its shape cannot change. So it's going to be something like this. And now this contrast, or this difference that we have about the flexible structure and the rigid structure, this is what we can call indentation. And now, based on how much is this penetration, how much is rigid bodies penetrating? Because in reality, they cannot penetrate. You don't see that to happen in real life. You can see that too, but if you take a ball, you drop it top of the table, it's not going to go inside of the table and then bounce back. Now, this penetration is something we use to introduce this penalty force to kick things out. Okay, but again, this is penalty based. But in this constraint where you're going to use this inequality, is going to be more or less the same story. Okay, here are the two ways that you can describe the contact. So it's a penalty forces, which is smooth dynamics. Smooth dynamics. And non-smooth is going to be this complementary, which is based on these inequalities. Okay, I'm cutting the corners. The reality is much more complicated than this, but let me try to explain it in a way that you will capture the big picture. Okay, now penalty force is, like the title says, is based on these penetrating geometries. And then you're going to just introduce the force that is a function of the penetration. This one here, how much they are overlapping. Now, this is a method where you're introducing simple function like this. So it's going to be a function which is based on the stiffness, which you assume to be based on your materials. Often actually it's not based on your materials, but based on your computational parameters. And why is that? Gonna explain that in a second. And then you have this x here, which is describing how much is your penetration, power n. Power n is like what is this exponential that is describing how much force is gained based on the penetration. It's very common that n here is not 1. And it's not 1 because there's a discontinuity if you're going to use a 1. And that's simply because if I'm going to take a look at the, how is this force versus the penetration, it's going to be linear curve like this, which is okay. But we have a problem when I'm going to take a close look about this corner here, because this corner here, I have here penetration, and I have here force, and I'm coming to this corner like this, meaning that this is going to increase, or this is when the forces are started to develop, when the two constraints, or where the two geometries are overlapping. But when they are not overlapping, it's going to be like this. This one here is discontinuity. This is a discontinuity that is not well received in the numerical integration scheme, because it can recognize this discontinuity and it started to make a trouble out of it. So you can smooth this. And way you can smooth it is that you use n that is something else than a 1. If this is, for example, 2, you see that they are progressing in a way that this corner here is smooth. You're progressively increasing the force that are separating them from each other, and that's how you can get rid of the problem. Okay. Now here's this is just a simple ball is conducting the plane. Okay, this is what we discussed earlier. So this is how it behaves. But here's another example that was made by Jussi Sopanen a million years ago. I don't know if you know this. This is one of the early versions of the Ropedin, if you know this software. You never heard it. Okay. Anyway, so it's a software that you can analyze rotating structures, including bearings. Now the bearings that you can see here, this is a ball bearing. The bearing forces between the inner ring and outer ring were based on these penalty forces. So based on like how much they are penetrating, and based on this penetration, the forces are displayed and computed as it is shown here. How this works in details, it is actually shown in this slide here. This is a lot of details, a lot of complications, but take a look at what matters here. This is force equation. How much forces are imposed between the ball and inner and outer ring. And you see that this here is a stiffness, like was the case in the previous slide. This one here is a penetration that is displayed, or excuse me, computed based on oil thickness and so on and so forth. This stiffness here was based on geometry and material. And then this one here, the n here obviously is 1.5. Okay. And then there's a lot of details that automatically creates these contact forces for you. And you just need to top the best scenarios. You just need to top the bearing type, and rest will be automatically obtained from the library. And if you don't have this in your library, then you need to do the computing by yourself. I mean, introducing the forces by, not forces, but the initial parameters by yourself. It works like this. You have, this is a shaft that is partly invisible. At the end of the shaft, there is a force that is rotating. And then there is a reaction force. And if you take a close look about this reaction force, this one here, this guy, which is moving, now that it is here. So it's fluctuating all the time. You see that. So it's not having the same value than this one. This was 1,000 newtons, and this was 1,000 and sometimes a little bit else, something else, and there was this moment as well. This moment and this reaction force were fluctuating all the time. You notice that? I think you notice it, right? Okay. You see they are fluctuating. Both of them are fluctuating. And this is simply because this model was capable to describe this situation that you have a ball like this, And the force is traveling to the ball like this, which is different when there is a two balls like this, and the force is traveling like that. So the stiffness was varying because of this fact. And you see that in the reality too. And then you were able to introduce different kind of initial conditions to see how it behaves, also initial cracks, initial inner ring that is not perfect in a shape, and this is where the crack is traveling. I don't know if Jussi already introduced this to you. He did not. Okay, anyways, the reason that I'm introducing this is all based on these penalty forces, and it's pretty advanced. Of course, this computationally slow, it's not very efficient, but the penalty forces can do for you something like this. So it can be used even in a bearing modeling and many, many million other applications. So it's pretty powerful thing, but comes with the limitation. And the limitations is that it's okay to deal with the limited number of contacts using the penalty forces. It's no longer very efficient if you have a lot of forces and a lot of particles that can interact with each other. So let me take myself back here. If you have a system like this, limited number of balls, it's going to be okay. But if I increase in the number of balls to be, let's say, 1 million, it becomes to be a little bit unstable. And it also becomes to be unstable if there's a lot of differences between the masses of the balls. So if there's one ball very big and the rest of the balls are very small, this mass difference makes it this hard to be used, because then the force that you can create between these different sizes of obstacles becomes to be so large that the small ones will fly too much and they becomes to be unstable. And you easily see that if there is a penalty-based formulation, if there is a sand or rock bile, these rock biles are moving easily. They started to move a little bit with respect to each other. And this kind of small movement can increase, that they can start increasing the forces that are increasing, and then the one rock is rapidly flying off from the pile. That can happen when using these penalty forces. This is very sensitive for time integration settings, particular time step that you take. And that's easy to understand. If you look at this scenario here, I have here a surface and a ball. And now the time step you're computing this is big. So the delta t is very big, such that in our first time step, the ball will be here. Second time step is going to be here. Third one is going to be here. Take a look at the amount of penetration. So it's huge. Penetration is huge. And now if this is a steel material, ball is a steel material, surface is a steel material, the force produced by this system is going to be enormous in size. It's going to kick this ball so far out of the space that you're never going to find it anymore. So you need to make sure that your time step is as small as possible, not to make these kind of things to happen. So it's unstable in that sense. All right. Here comes my last, okay, simple to use. Integration settings need to be selected with care, because it can lead to the problems that there's too much penetration, unrealistic amount of penetration, and because of the large penetration, remember the force is a function of the penetration. Now, too much penetration, too much forces that are separating the bodies from each other, they can fly too far from each other. The mass difference is limited as well. So you cannot, it's going to be hard to use a tank that is rolling over with the sand surface. For two reasons: the mass differences are too high, and this is not very efficient if you have a lot of possible contacts. Okay, my in-class quiz is this. Contact forces can be described using penalty forces. Drawback associated with this method is damping is difficult to describe. Multiple contacts are difficult to describe. Method is sensitive for integration settings. Very good, by the way, demonstration about how well you listen to me. Because I was just repeating this, I was explaining this in my previous slide. But I'm not going to take myself back here, but instead I'm going to take myself to, where is it now? here. And I'm going to move on to next in-class quiz. Contact forces. And then we're going to take a look at the last one, which is based on this cone complementary. Okay, this cone complementary is very complicated story, and I want to cut the corners when I'm explaining. But basically, we just kind of like saying that there are constraints. No, I'm not sure if this is the right way to say it, but it's like inequalities that are preventing this contact to take place. And that's why they're non-smooth. Non-smooth requires special integrators to be handled. And that's possible too. But then it makes possible to describe very high number of particles, really high number. Okay, but the first one is this one here. What is the problem with the penalty forces? Ah, yes, of course, of course. There it goes. What's that? 100. Okay. No, there is a guess that it's gonna be no, no. Well, this is a lottery. That's 100% success rate. That would be a miracle. That would be a miracle. So I don't know how can you really handle that much of a dancing? I don't know. Okay. Um, okay, we got 19. So it's I think we could be okay. So can I close this? I think that I can. Okay, you guys are saying 100%. 90, 90. Okay, I'm saying 100%. Huh, 85. 85. Okay, multiple contacts is okay. So it's not a problem. It's okay, so you can do it. It's possible, but the problem is sensitive for integrated settings. That's what the big problem is. Okay, and now what we're gonna do is we continue here, and it's gonna be the last subject matter, which is this cone complementary approach. And before we're going there, so there's one team that is located in uh, Madison, Wisconsin. They're very good in this method. So let me show. They I have another video that is related to that, but this guy is doing things related to this cone complementary and non-smooth dynamics. So let me try to show you how much particles they are able to handle because it's a lot. This is a um, granular dynamics. Maybe it's this one. Okay, these are the all particles here. There is so many of them. You see that you got a little bit of peak, like how many particles is there? Okay, let me try to take another video. There's a lot of particles. What about this one? Look at how many particles. If you would like to model this by using contact, this penalty force is going to be a lot of work for you. Maybe too much. Same here. Look at how small are the particles. Very, very small. Good example of what is the case here. And then this one is the last one. Again, a lot of particles. It's almost like a fluid. And they're using that in fluid dynamics purposes because it becomes to be so close to the fluid that this is not possible. So they're using millions of particles. And that's why they call this method as a many-body dynamics, not as a multi-body dynamics, but many-body dynamics, because I don't know where is the limit. But the thing is that they're describing the contacts in a different way. That's what makes this many-body dynamics instead of multi-body dynamics. Okay, now maybe I should use this presentation mode here. Okay, now what we're doing here is that we are we are, let me see. So we have this measure that is measuring the geometries, how far they are from each other. And this is now this, what is this? Phi? What is this? You know, you need to help me. What is this called? Okay, I need to take another, this guy, which is phi equal to 0. Is it phi? Phi, phi, phi equal to 0. So now this is what you're measuring. So you're measuring this phi, and you want to make sure that this phi is always positive. And how you're going to do that is that you have this kind of the contact description here. Okay. Is it because of my connection or what? Why it is doing that? Because it's blinking like no limit. Now it's saying nothing anymore. Oh, no, it's a duplicate. What just happened? What happened here? Because now is a, was it there or no? No? It looked that the projector died. Oh my God. Yep, now it's back. But I see nothing in my screen anymore. Oh, this is so weird. Oh yeah, I see it. Okay, we're back. We're back. Okay. All right. So these are the, okay, so very, very complicated story, but so what we're going to do is that we're monitoring the distance between the neighboring bodies, like here, and then we wanted to make that to be positive. And here's an example that was computed. This is a planar case, and this was based on this cone complementary. So you see that they don't penetrate, but these inequalities make them separated, and you can. This is an alternative way you can describe the contact. This is this professor we looked a little while ago. He's explaining what is the deal with this cone complementary approach and non-smooth dynamics. Let me see if you can hear this.
Good afternoon.
Oh no,
My name is Dan
no.
Groot. I'm an assistant professor at the University of Wisconsin.
Hmm. How can I make this in a way that you can hear this? So I have everything is okay here. Oh, so it's going to my headset. So let me try this one. Still nothing.
Good afternoon. My name is Dan Groot. I'm an assistant professor at the University of Wisconsin in Madison.
Can you hear this? You can hear that. Okay, let me just try to make this guy to cooperate. Then soon we are off today. So okay, this guy.
And I want to start by thanking you for taking
Ah,
the time to attend my presentation here. I'm going to
no
talk
more
about
voice.
this topic of
Okay, it's either you or online participants. I see that.
medicine, and I want to start
Okay,
by
so what I will do is that I will send this link to you. So take a look at this video. Is a lot nice, really nice video about what is a many body dynamics, and what's the deal with the whole thing. So please take a look. I'm gonna email that to you via this Moodle communication thing. So you can have a link that you can just click. No need to type the link because the link will be complicated to use. Okay. Now here's what I promise you, what I'm proposing to you. So if you promise to take a look at this video, so it's going to be what it says. I think it was like 7 minutes. So we can close earlier now, and you just go and take a look at this video, and then we're good. And then a week from now, we're going to take a look at the stress analysis based on multi-body system dynamics and what's the deal with the fatigue analysis. Can you be here? Because I would like to hear your opinions about how is my story versus the course of fatigue of what? What is the course name? Fatigue analysis or what? Fatigue analysis. Very good. Very good. Okay. So can you please be here? Okay. All right. So here's the promise. So the link will be momentarily in your inbox. So take a look at the link. And with that, I'm gonna close for today. And we're gonna see you on next week Tuesday, and we continue with the stress analysis and fatigue. Good. Any other comments, questions? Okay. Thank you, guys. And let me go here to close